Hi, I'd like to talk to you about interactive shallow Clifford circuits, quantum advantage against NC1 and beyond. And this is joint work with Daniel Greer. So I'd like to start by breaking down our title. So we're trying to prove a quantum advantage, show that some quantum device can do something that a corresponding classical device can't. And the problem we're going to use for this is interactive. Meaning that there are rounds of communication back and forth with the device. So that's a bit unusual. On the quantum side, the class we're going to be looking at is constant depth quantum circuits, and specifically ones that are composed entirely of Clifford gates. And then on the classical class, we'll look at various complexity classes, so log depth classical circuits, NC1, and beyond. In particular, log space and a class called parity L will feature prominently. So that's it. We're proving a quantum advantage with an interactive problem. So what's already known about these shallow quantum circuits versus shallow classical circuits? Well, the work to look at there is Bravi, Gossett, and Koenig 2018. So they introduced what they called the hidden linear function problem, and we'll see more of that on the next slide. But the result was that constant depth quantum circuits solve this problem, yet constant depth classical circuits do not. So we've got this fair comparison between, constant depth quantum and constant depth classical, and we get a quantum advantage. Now, following this paper, there was a paper by Benewatz et al. That extended it just a little bit, gave the classical circuits more power. So they're still constant depth, but they have access now to unbounded fan and AND gates and OR gates instead of just 2 input ANDs and 2 input ORs. And this class is known to be larger than the other one, and yet they show that it still cannot solve the HLF problem. So now it's even an unfair comparison. In the classical device's advantage, it has these big gates that the quantum device doesn't have, and still there's a quantum advantage. So the question then is, how far can we push this? What's the largest complexity class that can't solve HLF? Or if we switch to some other problem, can we make an even more dramatic separation? Well, let's take a look at the hidden linear function problem and get a feel for how difficult it is. So originally, it was defined by BGK in terms of a quadratic form. And there's a linear subspace hidden within this quadratic form on which it's linear. And you have to find the linear subspace and the linear function and report its coefficients. It's a bit technical to define formally, but then the authors go and present this beautifully simple quantum circuit for the problem. So we're going to actually reverse this, and we're going to present the quantum circuit first and use it to define the problem. Okay, so we'll present this quantum circuit, and the problem will be to do what the quantum circuit does, or output any string that this quantum circuit outputs with some positive probability. And I want to stress that it's not a sampling problem. We're not asking it to match the distribution of the quantum circuit, just output something plausible. Okay, so next step then is to define the quantum circuit. So it's very simple. There are 3 steps. The first one is to start with a grid of qubits in the plus state, so a uniform superposition over all 0, 1 assignments to these vertices, essentially. And then we're going to apply entangling gates, CZ gates specifically. And the thing you need to know about CZ gates, they're a 2-qubit Clifford gate, and all of them in this diagram will commute with each other. So it doesn't matter what order we apply them, just which subset of the gates we apply. And that's determined by the input. So we get a bit for each edge, either a 0 or a 1, that tells us whether to apply the gate or not. Okay, so that's step 2. And I should note that we can apply all of the gates in at most 4 layers. Basically, you can 4-color the edges of the grid graph, and then you apply all the red gates simultaneously, and so on. All right, step 3 is we measure the qubits. What else is there to do? So we'll measure in either the x basis or the y basis, and this is determined by yet more input bits. So now we have an input for each vertex, and it tells us which basis to use. And that's it. We get measurement outcomes, say 0, 1 outcomes, and we concatenate them together, and that's the string we return. And surprisingly, this has something to do with quadratic forms and linear functions, but it's, in my opinion, much more easily described with this quantum circuit. So, how hard is the hidden linear function problem? Can we use any of this to, say, upper bound the difficulty of it? And it turns out we can. So, there's this theorem of Aronson and Gottesman that simulating Clifford circuits is parity L complete. And everything we just saw is Clifford. We start in a stabilizer state, we apply CZ gates, and then we measure in a Pauli basis. That's perfect. So all of this can be simulated in parity L. Now parity L is a bit of an unusual class, so I should define it. The formal definition is that it's based on whether there are an even or odd number of accepting paths in some non-deterministic log space machine. Sort of like parity P, if you're familiar with that, except log space instead of polynomial time. But really, the practical definition is that it's the class for all linear algebra tasks over F2. So determinant, rank, inverse, iterated matrix multiplication, various LU decomposition, for example. All of these are not just in parity L, they're parity L complete. Okay, so linear algebra, and that's not surprising. Remember, HLF was about a quadratic form and a linear function. It's not surprising it can be solved by this class. All right, good. So just for a little more context, here's a hierarchy of complexity classes. So each one is contained in the next, and the conventional wisdom is that they're all distinct. All the containments are strict. Let me point out a few of the classes we're interested in. NC0, constant F classical circuits. That's what appears in the BGK result. And the Bennett-Watts result upgrades it to AC0 with these unbounded fan-in and OR gates. Then we get to NC1, which is our class from the title. And parity L is the upper bound we just put on HLF. And just for a bit of perspective, all of these are contained in NC2, which is contained in P. So they're all still very small complexity classes. Now, given all that, where does HLF fit into this picture? Right? We know it's not in the top two classes because of the BGK result and Bennett-Watts. And we know it is in parity L, and thus all of the last three classes, by Aronson and Gottesman. But we don't know about NC1 and L, log space. And so Daniel and I have thought about this, and we couldn't figure out how to put the hidden linear function problem in L or NC1. So we think it's not in either of these classes. But how do we go about justifying this, right? It's not very convincing to say we just tried very hard. So the usual tool for this in complexity theory is to prove some kind of hardness. For example, we could prove parity L hardness. And then, well, this is a basic consequence, but basically HLF is either in L or not in L. It's got to be one of the two. But if it's in L, then we get this complexity theory collapse. L equals parity L. And that's unlikely. That contradicts the strictness of the containments in the previous slide. So that's evidence for the alternative, that HLF is not in log space. And you could do the same thing for NC1. So it's tempting to conjecture that HLF is parity L complete and try to prove it. And indeed, if I had to describe our main result in 6 words, they would be HLF is morally parity L complete. But you can see from the fact that I snuck a morally in there, and there are 3 asterisks hanging off the end of this theorem, that really it's not such a good conjecture. I'd go so far as to say it's almost certainly false. So the rest of the talk is going to be about reconciling this apparent contradiction, right? That the conjecture is, we think, false, and yet it's a fairly good description of our main theorem. So we're going to have to get into sort of the nuances and details of our theorem and explain how the two are different. And there are sort of 3 points. One, we're going to use an interactive version of HLF. Shouldn't be a surprise. It's advertised in the title. 2, our reduction only applies to classical solutions. Now I'll show you what I mean when we get there. And 3, we need randomness in our reduction, which I feel should be in the theorem statement. Okay, so let's start fixing our theorem. Get it closer to what we prove in the paper, which should be correct. Okay, so we're going to define an interactive version of HLF, and we're going to do it the same way we did with HLF. We're going to define a quantum circuit that solves the problem, and then the problem will be to do what the quantum circuit does, mimic it as close as possible, but not necessarily sample. And the quantum circuit itself is going to be very similar as well. So we're going to start with a grid of qubits in the plus state. We're going to apply CZ gates between all nearest neighbor pairs. We're just going to apply all of them. There's no input for it this time. And the state that we construct at this point is called a cluster state. So remember that for later. Now, step 3, we measure nearly all of the qubits in this cluster state in either the X or Y basis. So unlike HLF, we keep a constant number of qubits at the end. We reserve it for later. So we measure them, we get outcomes and report them back, and only then are we told how to measure the remaining constant number of qubits. So we do that and return those answers. So the main difference here between this and regular HLF is that we've split this measurement phase up into 2 steps, where we're told how to measure one half, well, not half, it's most of the qubits, and then we're told how to measure the last few remaining ones. So here's another diagram in case that helps. So we're sending information to the quantum device, it measures and returns the outcome. We're sending a few more bases, it measures and sends the outcomes back again. So now if we fix up our theorem, it says something more like interactive HLF is morally parity L complete. But we still need that morally. It's not really correct yet. Not really correct yet. So let's keep fixing it. Now I claim we need the reduction to only apply to classical solutions to the interactive HLF problem. So to see why, let's think about what happens if we had the reduction we want. Suppose interactive HLF is parity L hard, and for concreteness we have AC0 reductions. So what that would mean is we could plug in the quantum solution for IHLF. Right? We know a quantum circuit, constant depth quantum circuit, solves this problem. So let's plug it in and see what the reduction tells us. And basically what it tells us is that some combination of AC0 with an oracle to QNC0, that's not quite accurate, but pretty close, solves parity L hard problems, okay, and thus all of parity L. Now we couldn't find a conjecture in the literature that says this is a bad idea, but we don't think this is possible. It's just too much power for constant depth circuits. So we need to avoid this. We need the reduction to only work when we plug in like log space so we can get that contradiction we're looking for. Okay, but that's not usually how reductions work, right? Usually reductions are pretty black box, completely agnostic to where they get the solution from. So, fortunately we have an ace up our sleeve, which is interactivity. So this is a sketch of the interface between the user and a sort of black box device that solves the hidden linear function problem. So basically we send it an input, we get an output, we send it the second round of input, we get the second output, and then we're done. But since we're not going to limit how many times we can use this device, we also have the option to reset back to the beginning and start a new round. All right. But just as a thought experiment, what if we feed it an input and get the output, and then we stop in the middle of this procedure and just open up the device. see what's inside, because whatever's in there is describing these constantly many qubits that are left over. In the case of the quantum circuit, it's literally the qubits themselves. But in a classical device, it's going to be classical information. If it's, say, a log space machine, then there's the tape contents and the position of the head and all of that. And since it's classical information, we can write it all down. We can make a copy, a backup, a save point in the middle of this interaction. And then we can proceed on. We can, say, ask for X basis measurements on all the qubits, and it'll tell us the answer. And then we have the option to reset back to the beginning, but we can also rewind back to the end of the first round, right? We have the state of the machine at that point. We can just set everything back up the way it was and run it again. And this time we could ask for Y basis measurements and get those outcomes, and so on. Okay, so we have this rewinding ability. And it's pretty general, right? If a classical device solves an interactive problem, then pretty much we can rewind it. And often we can rewind it with the same complexity class. Now there are exceptions, but it is at least true for NC1 and L that we can rewind within, that is, if an NC1 or L device solves the interactive problem, then we can also rewind in that class. On the other hand, quantum device, the no cloning theorem will prevent us from copying the qubits. We get to measure them once and only once, and that's just enforced by the laws of physics. So there's no getting around it. Okay, so then the new revised theorem is that rewindable interactive HLF is parity L complete. So now this reduction only applies to classical devices, because if we have a quantum device, we can't convert it from the basic interactive problem to the rewindable version. So that's how we do it. And now this theorem is pretty close to being correct. Let's try and prove it, okay? So the first step is we're doing a reduction from some parity L complete problem to rewindable interactive HLF. And that means we need to choose what problem we want to start from. There are many parity L complete problems. So the one we'll choose is to simulate a circuit of C0 gates. So you have some circuit of C0 gates, and you're promised that when you multiply it all out, it's either equal to the identity or C0, just one C0. Okay? I think that's actually false for this example, but whatever. All right, so then that sounds like a good idea. We're simulating a Clifford circuit with a Clifford circuit, but there's still a bit of a mismatch. Our interactive HLF problem is about a shallow circuit using only CZ gates. How are we going to simulate a deep circuit that has a bunch of C0 gates? Well, this is where we're saved by a theorem of Rausendorf, Brown, and Briegel. So they came up with this idea of measurement-based quantum computing, which says that we can simulate any quantum circuit we want just by measuring a cluster state. And for Clifford circuits, it gets even better. It suffices to just use X and Y basis measurements. And this is perfect, right? Interactive HLF, we construct a cluster state and then we measure it in 2 rounds in just the X and Y basis. And conveniently, that simulates a Clifford circuit, which is precisely what we're trying to do. However, there is a catch. The catch is that Pauli errors are inserted at random after each gate. So what we end up simulating is not the C0 gate circuit itself, but something like this, where there are errors all over the place. And the errors are pretty bad. The classical analog to this is applying a NOT gate after each gate with 50% probability. It just eradicates all the information in the circuit, right? So the error rates here are much too high for us to use an error correcting code. Some of you may be aware that you can push Paulis through Clifford gates, and that's an interesting strategy, but just pushing all of them through our circuit, in this case, would be parity L hard on its own. And so we can't afford to do that in our reduction. But there is still some information that survives these Pauli errors. So if you look at these two circuits, right, they have a bunch of Pauli errors, and in the middle we have either nothing or C0, precisely the two cases we're trying to distinguish. And basically, one of them is separable, the top one is separable, and the bottom one is not. And this is in spite of all the Pauli errors that can happen. So we've got the outline of a theorem, or a reduction here. Basically, simulate all of these C0 gates, the whole deep C0 sequence with MBQC in the first round of the computation. And then we'll have this 1 or 2 qubit state, or 2 or 3 qubit state in the paper available to measure in the second round. Okay, and then we'll do some measurement somehow to determine if the state is separable or not, and then we're done. We can output the answer. Now I should point out that in the second round, where we're measuring those last few qubits, we're not just restricted to X and Y basis measurements. We can do a sort of mini MBQC round there and get arbitrary stabilizer basis measurements. But the question remains, how do we measure this state to determine if it's separable? Right? We have no idea what the state actually is, right? There's this, could be plus or minus, 0 or 1, or entangled. There's lots of possibilities because of the Pauli errors, but we want to figure out if it's separable. So what can we do? Well, some of you are familiar with quantum tomography, which lets you learn a d-dimensional quantum state in about order d squared measurements. But for stabilizer states, you can learn it exactly, so perfect. And rewindability of our circuit, so we can measure in the second round as many times as we want, gives us repeated measurement. So this all looks very promising. It looks like we should be able to do quantum tomography and just learn the entire state of those qubits. And then it'll be trivial to distinguish whether they're separable or not. But, of course, it's not so easy. All of the tomography techniques I'm aware of require samples from the distribution. Like you have to actually get samples from the measurement distribution of your quantum state. And they could fail, right? If you get unlucky with your measurements, very, very unlucky, you might not learn anything about the state. So since our problem is not a sampling problem, we have to account for that case. We have to account for the possibility that we always get the least helpful measurement outcome. So there are two ways to deal with this. A lot of people, when we explain this result, say, why don't you just make the interactive hidden linear function problem sampling? Just make a sampling version and work with that instead, and then you can use this kind of tomography and you're done. No more steps. But the downside of doing that is that to make the sampling work with rewinding, you need sort of an unreasonably strong condition, and it's not pretty, trust me. So what we do instead is we come up with a different scheme. Basically, we use the magic square or magic pentagram, sort of quantum contextuality ideas to force an inconsistent answer from the device. And that tells us a tiny bit about the state, really more about what the state is not than what it is. But then there's a randomized self-reduction we can do that guarantees we learn a random piece of information rather than a perhaps adversarially chosen piece of information. So the third kind of tweak we need to make to our theorem is that the reduction is randomized. And then last, we just accumulate these pieces of information by many parallel applications of this, and eventually learn the whole constant qubit size stabilizer state, and then it's easy to decide if it's separable or not. And then we're done. We have the answer. We've solved a parity L-hard problem. So our final theorem then is that rewindable interactive hidden linear function problem is parity L complete under randomized reductions. So let's use it to solve a simple problem to show that log space can't solve it, for instance. So imagine for a contradiction that interactive HLF is in log space. Since log space is well behaved and classical, we get that rewindable interactive HLF is in log space. And since our reductions are randomized, they're actually in the class BPAC0, then that class with an oracle for L contains parity L problems, can do anything. So the only thing L is getting from BPAC0 is the randomness, so we can replace it with just randomized log space, right? And we could stop here. Randomized log space containing parity L is already weird, but if we give it both of the classes advice, then we get this inclusion of non-uniform classes, which is kind of nice. It subsumes the randomness. And so the interactive HLF problem is not an L unless we have this collapse. And I just want to add that we also have similar results if you're working on a smaller grid. If your quantum computer doesn't have enough space for an n by poly n grid, you can get away with a 2 by n or 1 by n grid. And we get results about weaker classes. In the second case, we even get a result that's unconditional, because the classes, we can prove the complexity class collapse does not occur. Thank you.